Hello, good evening, everyone. Okay, so good evening again. Welcome to the live session 3 of non-conventional energy resources. So I think we should start now because most of you have joined. And so, have you guys gone through the weekly material that has been uploaded on NPTEL? Okay, guys, let's start the session. So, am I audible to you all? Can okay. So, welcome again to this live session 3 of NPTEL for the course Non-Conventional Energy Resources. This course is uh, being taught by Professor Pratap Haridos from Department of Metallurgical and Material Sciences in IIT Madras. I am Rohit. I am a research scholar in IIT Bombay. I'll be taking this live session. So how I have planned this live session is that we will first go through the questions in non-graded portion of the assignment. We will discuss those questions. Then we will move towards the graded question of the old assignments, not from this assignment which you have been given in this week, but from the old run of this course. So we will discuss these assignments and we'll take up your doubts and anything you want to ask in between, you can ask in the discussion forum, or else you are always permitted to ask in between the live sessions also. So these live sessions are basically an interaction session being planned between uh, course TAs and your student, so that somebody wants to join. So in between, if you want to ask any questions, you are always welcome to post your question in call messages, which you can see in the right hand side, or else you can turn on your mic and ask in between also. And try to ask as much question as you can, so that we can have a fruitful discussion, and also can go through the ways or different topics, and it will make you better understand those topics on a much larger scale. Okay, so let's start this live session. Okay, so the first question of this live session is that the size of the planet decides how much energy from sun reaches the planet given a fixed orbit. So, if we see this question has the size of the planet, like it is talking about a planet like Earth, okay, and it is saying that how much energy from the sun reaches that planet given a fixed orbit. So, if this is a sun, like this is the center of our solar system, so you know all the planets revolve in elliptical orbit, like here or some other orbits. This question has some how much energy it must be a fixed quantity of energy reaches from sun. This must be the question. Okay, the size of the planet decide the fixed energy or how much energy. Okay, the size of the planet. Okay, so whatever energy is reaching from sun to this planet very much depends on the size of the planet. Okay, because the size of the planet will have, as the planet size grows, it will have a larger surface area to receive the portion of the sunlight or the sun irradiation on its surface. Okay, so size of the planet very much matters when you talk about the how much energy you can intercept from a sun. Okay, like if you see from a simple example, like this is the sun. Okay? This is the sun, and this is a small planet. Okay, so sun is giving energy, and this is a large planet. So you can imagine this planet can only trap this much amount of energy, but if you talk about this planet, this can trap a lot more amount of energy than this planet. So size of the planet is a important criteria in deciding how much energy from the sun reaches the planet given a fixed orbit. If the orbit is changing, then this energy can also vary. Okay, so this statement is basically true, and we need to discuss certain concepts here, like what is a orbit basically. So orbit is basically a path in which the planets revolve around the sun. So the planets doesn't revolve in haphazard manner or random manner. They revolve around the sun in some predefined or well-defined structured path. Okay, and these structured paths are called orbits. And second is, I want to ask for your practical knowledge also, how far is sun situated from Earth? So if you see the distance between sun and Earth, so if it's Earth and this is sun, center to center distance is something around 1.5 into 10 to the power 8 kilometer. Okay, so this much is the distance between sun and earth. So you can see sun and earth is situated at a much uh, very much larger distance from the sun. So to trap the sun's energy, uh, earth has to have a perfect alignment with the sun. So there is a term also, solar constant. So we will discuss as we move through this lecture, we will discuss these specific terms like solar constant, how much is the earth solar energy budget and everything. Okay, so we'll discuss one by one. Another thing is like a quick tricky observation, like whether the planets revolve around the sun in circular or elliptical orbit. Okay, so for your understanding, the planets revolve around the sun in an elliptical orbit. So it is not a circular orbit like it has been believed earlier, like some 400 or 500 years earlier. Maybe much more before that, the Earth was uh, observed to be the center. Observed, no, you can't say observed. Earth was believed to be the center of this whole solar system or universe, but that is not so. Sun is the solar system, and all the planets revolve around it in some elliptical orbit. Okay, so that is why we have variation in solar energy gain on the planet, and also the variation in seasons, so that can be explained through this elliptical orbit movement of the planets. So if there is any question regarding this question one, you can ask me or you can post it in the forum so I can see. Let me see if anybody has asked a question. No, nobody has asked a question. I think most of you have understood the concept. So if there is anything you want to ask, you can ask freely. We can have a free discussion here. So if there are no questions, then we move to the why planet move around sun, Vishal. Okay, so this is a very important question. Why planet move around the sun? So you have studied about the centrifugal and centripetal forces. Okay, so basically there is some space-time and gravity concept here also. Maybe I cannot someone from physics background maybe explained in much better way. But the main reason for planets moving around the sun is that the sun attracts these planets through gravitational forces, and due to these gravitational forces, a centripetal force act on the planets that balance these gravitational forces. So that's why it's like a string, so a stone attached to a string. As long as this string moves in circular direction, the stone also moves along with the string. The moment you stop the string, the uh, stone also falls down. So similar is the thing. If planet stops moving, they will fall down in the sun, crash in the sun. Okay. So these forces, the balance of forces make them these planets move around the sun. Hope I have explained it, Vishal. Maybe some other things also can be seen, like in Albert Einstein and many other scientists have given this space-time phenomena also, space-time dimension, like space xyz is a dimension and time is also a dimension. So there is uh, explanation that when sun is situated, sun is a heavier object, so it makes a much heavier imprint in the space-time domain. And similar, planets like Earth has a much smaller domain than Sun or mass than Sun, so their space-time uh, pitch is much small. So some on these lines concepts are some concepts on these lines are there and very much explored in physics domain. So we are not going into that. But for your understanding, I think you can also read this space-time thing. So this is a very interesting concept. Okay, so let's move to question 2. So let me take a pen. Question 2 is that there is a close link between GDP of a state and the power consumed by the state. So this is a very important question considering our course. So it is saying that GDP of a state, if we take a GDP of a state, the power consumed by a state has a very close link. Like if we have increase in GDP, then power consumed will also increase. Okay. So yeah, this statement is true. Why true? We will discuss. So as the GDP is increased, so this statement is true, correct answer true. So as the GDP is increased, GDP is basically what? GDP is basically the amount of services and products formed within the domestic territory of a nation like India. Okay, if you take India, see this box represents India. So whatever products and services made inside this domain or territory of India is counted in GDP. Okay, so how do we count them? We convert these products and services in monetary terms and then we add them up. So that is the GDP. Okay, so talking about the state, so you can instead of India you can take Maharashtra, Uttar Pradesh, or any state which you want, or Tamil Nadu. Okay. So as you see that if the GDP increased, the power consumption will also increase. So why so? Because GDP is very much linked to the consumption pattern. More products are formed. So industrial also, economic also, okay, political also in some sense. So these stability leads to increase in GDP. So if you have a good consumption pattern, good industrial output, so that always contributes to the GDP. Okay, and as the GDP increase, because we have more industry, more residential houses, more people living there, urbanization is more. So these are the things which require power for its operation. So that's how the power consumption will also rise with the GDP of the state. Okay. So a simple example you can see, let's remove this state and substitute it with nation. So we see that USA has a GDP of something 20 trillion dollar. China has a GDP of something around 12 trillion dollar. How much is the GDP of India? Can anyone say? It's around 2.97 trillion dollar. And how much is the energy consumption by USA? 20 kilowatt hour electricity consumption per capita. China, it's something around 8 to 12 or something. Okay, India something around 1 to 2. So you can see as the GDP increasing 22.9 to 12 to 20, the power consumption also increased from 1 to 2 to 8 to 12 to 20. Somebody wants to join. Is there any questions? So as the GDP increased, we saw that as the GDP increased for USA, India, China, comparable GDP increased this, the power consumption was also moving in this direction. So they are very much closely interlinked. Based on that, concept is there of energy poverty. So it's basically uh, countries like very small countries or something, they cannot afford energy, or people they cannot afford energy. So because so we were talking about energy poverty. So some countries like Zimbabwe, Venezuela, or something, they have recent example is Sri Lanka. They have a very you don't have a very high per capita income. So these countries or the people are so uh, they cannot afford to buy energy on any terms. So there is also a concept of high grade and low grade energy. So these things come into picture when we talk about energy poverty. So it's a very big dimension of study, the energy poverty. These things will be discussed, has been discussed very elaboratively in the weekly lectures. So I will suggest you all guys to go through these terms: energy poverty, GDP of the state, power consumed. Also, if you see the developed versus developing countries, so what do you think? As the GDP goes up, uh, has a more power consumption, developed or developing? So based on the statement GDP of a state, so who will have a more GDP? Developed countries will have a more GDP, like USA, Sweden, European country, most of the European country, UK, France, a developing country like India, Bangladesh will not have so much of an industry or something like these countries. So they will have always a low GDP. So that's how these GDP thing is related with the power consumption. Somebody wants to move, join. Okay. So if there are any questions, you can ask it now, or you can post your question in call messages also. Uh, I can see your questions and I will answer it accordingly. Okay. So let's move to the next question, next concept. So I have also added a concept here. Like since we were discussing about GDP and power consumption, so yeah, we'll discuss this per capita energy consumption. We see that ki per capita energy consumption for USA is quite high, very much high, and it's quite low for India. Okay, and for China, it's on medium term or something, you can say, much lower than China. But if you see the overall energy, so maybe China will have a much higher than USA, then India, then Russian Federation, then Japan. Yes, so we see that decreasing trend here, but in per capita energy consumption, India has a much low. So what can be a possible reason for this? So it's talking about, basically this concept is talking about per capita. So what is per capita? We divide the total energy consumption or total annual energy consumption with the population. So as India has a very huge population, something around 1.41 billion. So as we divide the energy with the uh, population, the per capita energy consumption for India comes to be very low compared to China and United States. So that's how India is actually, when we compare this. Also, if we see this graph, one more thing is clear, that countries like United States, Russia, Japan, these are highly developed and highly economized countries, highly industrialized countries. So their per capita energy consumption is quite high compared to India and China. India, if you see that India has the lowest per capita energy consumption among them. So possible reason is India has less urbanization, first reason. Second is much lesser industry than these countries. So much less economic activity than these countries. So these things actually affect the energy consumption very much. So when you talk of energy consumption, it's a thing. So it takes it into account the urbanization, the economic development, the industrial growth, everything. Please, sir, explain more about energy poverty. Okay. Please explain more about energy poverty. Okay, Vishal, I will take this energy poverty thing after this question. I will, if I forgot, please remind me. I will discuss it more properly. Okay. So, that's how you see that this whole economic thing, like GDP, is basically an economic term. Takes into account the different the amount of products and services that is being produced in a country. So as the GDP is high, the energy consumption is also high. Okay, coming to the question three. This is a very interesting question. It talks about a very interesting thing or interesting concept here. Oh, somebody wants to join. See you wants to join. Okay, so everything is good. Okay, this question talks about a very interesting concept called Dyson sphere. So there was a scientist, his name was some Franklin Dyson or something. I don't remember his name. Please, go slides. He proposed a concept called Dyson sphere. So basically, this question is based on that concept only. Dyson, what is a Dyson sphere? And we'll talk about that Dyson sphere. So a hypothetical Dyson sphere will capture all the energy from the sun coming to the orbit of the earth. So this is the concept. And what is the concept of Dyson sphere basically? He actually calculated the different energy consumption patterns and estimated that within 3000 years we have will have exponential growth in energy requirement. So that much energy is similarly not available on Earth or any other planet, but due to the population growth, industrialization, and economic growth, everything, our energy requirement will be so high that we need to have a constant source of energy. So our constant source of energy is star, and which is our star? The sun is our star. So what we propose that a hypothetical sphere, this is the sphere which covers the sun in such a way that it traps all the energy coming from the sun from all the direction. So a sphere is a 3D object, so it covers the sun such that all the energy emancipating from the sun reaches this sphere and get trapped within the sphere for its utilization for different purposes. Okay, so that is what the Dyson sphere talks about. So since this concept was basically to capture all the energy coming from all the energy from the sun coming to the earth, so it is a true concept. But this Dyson sphere is hypothetical. Why it is hypothetical? The first question is why? Why hypothetical? Why it cannot be possible or why it hasn't been tried yet? Main reason is that the sun, you know the radius of sun? The radius of sun is 0.7 million kilometer. So imagine if such a big star is to be circled within a sphere. So how much should be the radius of that sphere? To build such a sphere is a quite difficult challenge for different types of star which is present in our solar system. So that has to be taken into account when we talks about this Dyson sphere or different other things or different concepts which goes into this. So that is why this concept is still hypothetical, being explored or being imagined that some alien beings must have thought about it and must have tried on their sun, on their star itself. Okay, so we talked about Dyson sphere here. Is it possible to have a Dyson sphere? So let's say that we have the technology to build a Dyson sphere. We have a sun. We have big machines and all the materials available for us to build a Dyson sphere. So is it possible to build a Dyson sphere? This is the main question. So if you think from engineering point of view or science point of view for this concept, so let's say, let me raise this and let's talk about this Dyson sphere a little bit because it's an interesting concept. So I am sure that you guys will like it. So let's say this is a sun. Okay, this is a Dyson sphere encircling it. So different rays are actually coming to this Dyson sphere. So what will happen after some time? Since this Dyson sphere is a solid object, it will have some thickness also. Okay. So after some time, what will happen? So all the energy that is coming to the Dyson sphere, some of these will be observed by the Dyson sphere, and some has to be reflected into this deep universe. Maybe in this direction or maybe in this direction, whatever direction it is. Some has to be reflected in this direction. Why? Because if we don't reflect, energy is coming constantly from the sun. So this Dyson sphere has a specific capacity of tolerance for heat, called heat capacity or something. So a temperature, this will lead to rise in temperature of the Dyson sphere, making it inhabitable for different uh, beings which are residing on this. So what will happen after some time? This Dyson sphere may melt or may break down if it doesn't reflect the energy back to the outer space of or energy or in the atmosphere. Okay, so that's how it has to be designed in such a way that whatever energy received, the energy utilized is being used in the Dyson sphere, then the extra energy is actually left out in the space or reflected, radiated out in the outer space. So that is how it is possible to build a Dyson sphere with thinking all about the possibilities of science that goes into it. So okay, no questions, nobody want to join. Okay, so I'm sure that most of you must have got a good sense here, okay, how this Dyson sphere has been imagined, okay, and how it has been thought about. It is basically to trap the energy of the star and to utilize that energy for our purposes. So for that only this Dyson sphere concept has come into picture. Okay. Now question 4. There is a strong need to change the source of energy used by the world. The question, first understand the question, what it is saying. There is a strong need to change the source of energy used by the world. So what is our source of energy as of now or as of 10 or 20 years before? So 10 or 20 years before, most of our energy is being fulfilled from fossil fuels. Okay, fossil fuels. We have coal, we have had oil, we have diesel, petrol, everything, natural gas. I think oil covers diesel, petrol. So we have this natural gas. So these were main energy sources that has been contributing for this world energy need. Okay, that is supplying for the world energy need. Now also the fossil fuels are major contributors or major suppliers of energy for the world, but renewable to some extent has also come up, maybe 10 or 15% for energy supply. Yeah. So what is the problem with fossil fuel? The main problem is that fossil fuels are uh, very like in a small quantity, so they will be depleted after some years. But if we talk about renewable energy, these can go for indefinite periods. So that's a huge addition to our resources also. And the second thing is that renewable energy doesn't contribute to the greenhouse gas emission or different pollution. So that has been the benefit for using renewable energy in the world. So yes, there has been a strong need to change the source of energy that is being used by the world. So these things has to be kept in mind when we wanted to use the different source of energy, or we will be thinking about the future source of energy. Okay, so this is quite a true statement. So the correct answer for it is true. Other thing is that when we talk of renewable energy, the capacity factor comes into play. Why capacity factor? Because renewable energy are mostly intermittent in nature, like solar energy. You cannot use solar energy throughout the day. You will have to have used the solar energy only in the daytime, or wind doesn't blow every time. So only when you have a constant speed of wind, then only wind turbine can generate electricity. So for that thing, this capacity factor term is a major capacity factor is a major term in renewable energy field. So what is the uh, capacity factor for this renewable energy or solar thing? It's generally zero point 0.3 or something for solar, maybe, or more less than that itself. But for fossil fuels, since this fossil fuel can be burned and can provide energy at any instant of time, so they have a very high capacity factor. Like for renewable, for not for nuclear or coal, it is something around zero point 0.9 to 0.96 something. So this is also an important thing. Another thing is that when you talk about renewable, you will have to have energy storage. Like if you have a sun, SPV, so you store this energy in morning. You generate electricity in the morning, you store it into electrochemical batteries, then at night from batteries using inverter it can supply during the night. So this is the main thing which can be utilized. So energy storage, so different research are also going on this energy storage thing, how this energy can be stored, how this energy can be utilized at a time when there is no renewable or something. So that is how there is a strong need to change the source of energy, but that has to be accompanied by increase in energy storage and capacity factor also. Okay, so is there any questions? Any question regarding this change in energy source or something? Okay. So we'll move to the next question then. Another next question is, the solar spectrum that reaches the surface of the earth is impacted by the gases in the atmosphere due to the wavelength that they observe. So if we see this question, the main concept is it is talking about the solar spectrum. Okay. The another thing is it is talking about ki whether this solar spectrum is impacted by the gases in the atmosphere. Okay, so if we see what are the gases present in the atmosphere, so most important gas is nitrogen, being a major composition of the gas. This is around 78%. Another one is oxygen. Then we have CO2, argon. Argon has a larger quantity than CO2, and helium, hydrogen, very trace amount or something. Okay. So these are the gases which are mostly present in the atmosphere, and when the sunlight strikes the molecule of these gases, the sunlight gets scattered or reflected back the atmosphere. Okay. So yeah, when the solar spectrum reaches the surface of the earth, it is impacted by the gases in the atmosphere. So this is a true statement. If we see the solar spectrum, so this is basically the solar spectrum which we see in generally for solar light. And when we move from left to right, there is an increase in wavelength. So we know that E. We know that energy from any wavelength is basically hc upon lambda. Somebody join. This is the energy content in light source or any light source that has some particular wavelength, that is moving with some particular wavelength. Okay, so basically hc upon lambda, we see that h is basically Planck's constant, c is speed of light, and lambda is the wavelength of light which we are talking about or whose energy is to be calculated. So solar spectrum basically has a whole range of light ranging from gamma rays, X-rays, ultraviolet, infrared, radio waves, and apart from that we have a very small range of visible light that varies from 400 nanometer of wavelength to 700 nanometer. As we move from violet to red, the wavelength increases, but the energy actually increases from left to right. Okay, so this solar wavelength is basically plays a very important role in heat generation or in solar PV. So if I ask you a question like how much should be the wavelength or how much is the maximum wavelength which solar PV utilizes for energy production or production of electricity. So this is basically 11 till 1100 nanometer. So it's not a hard and fast criteria that only up to 1100 nanometer, but for some material it can be high also. But for silicon, we can say that till 1100 nanometer, the solar PV cells can utilize the um, this radiation thing or wavelength up to 1100 nanometer to generate electricity. As we move move higher from 1100 nanometer, what happens? It generates some more energy. So this band gap between these two layers in semiconductor. So for semiconductor, we have a conductance band and this uh, valence band, and electron jumps from conduction band to valence band. So these things come into picture when we talk about the wavelength that can be utilized in solar PV. We'll get to know more about in upcoming lectures or week. I think in weekly lecture 4, Professor had discussed this concept. So please go through that, and we will discuss in the upcoming live session also. So this is what is utilized in solar PV. And basically when we move to this infrared region is basically a heat producing region. More and more heat is produced when we move to infrared region. Okay, and these gamma rays are more harmful for body. Like gamma rays can penetrate through thick uh, cartons or anything. So these gamma rays are basically radiation rays, so we need to be shielded from gamma rays also. So these are very small quantity, and most of them ultraviolet gamma ray x-rays are basically stored by the ozone layer, ozone molecules in the upper atmosphere also. So that's why this ozone layer thing is very important when we talk of these harmful x-rays, harmful rays. Now, the non-graded part of the assignment has been completed, and the next 10 questions are from graded part of the assignment of the previous run of this course. So, if there are any question in the non-graded part of the assignment, you can ask it now, or you can post it in the in-call messages. I can see those messages, and we can discuss these non-graded. Please, okay, no questions. Okay, so and let's take a break of 5 minutes. Then we'll move to the graded part of the assignment, and we will discuss these questions one by one. Okay. So, welcome you back after the break. Now we will discuss the graded assignment question of the previous turn of this. Okay. If there is any question you wanted to ask from the non-graded part of the assignment, you can post it in call messages, or you can turn on your mic and ask the question. Or if you want, you can also post this question in the discussion forum, so more students can benefit from your answers. Okay. So let's move to the non-graded part of the assignment. So the first question we see here is that the GDP of the nation increases energy consumption generally. So we had a long discussion in the first question itself. As the GDP of a nation increases, it has a direct impact on the energy consumption. So if the GDP is increasing, the energy consumption will also increase. So the correct answer is increase. Okay. And if we see that how GDP contributes to the energy consumption, so there can be various ways in which GDP can contribute to the energy consumption. Like if we have a high GDP, then certainly the industrial output is more. Somebody wants to join. Okay. So if we have a high GDP, then certainly the industrial output is more. Certainly the residential consumption of electricity is more. Why is more residential consumption? Because of urbanization. There will be cities, more cities will be developed that will contribute to the rising energy consumption. Another thing which can lead to increase in GDP is basically economic terms. So more trade, more something, more lightings, more consumption. So that also contributes to the GDP. And as the GDP increases, the energy consumption will also rise in the direct proportion. Okay? Now, if we see the energy consumption by various sectors, if we divide the world energy consumption and divide it among the different sectors of the economy. So one sector is that industry, how much energy the industry is utilizing, how much is the residential purposes. So industry and services, basically industry and different service sector companies. What can be the service sector company? Like IT companies, BPOs, IT call center, these type of things. Well, residential are basically the houses which consumes electricity, different types of houses in residential, urban sector, houses in uh, towns, small towns, villages, etc. Another thing which contributes for energy consumption is transportation. So this is one of the major contributors of energy consumption. Okay, so transportation like passenger vehicles, two-wheelers, three-wheelers, four-wheelers, bike, car, trucks, buses, aeroplanes, trains, everything comes under this transportation. Okay, so if we see the World Energy Statistics 2007, so it is published by International Energy Agency. So most of this energy consumption is by industrial and services sector. So as we mostly these sectors contribute to the GDP. Okay, so as the GDP rises, these sectors also rises. So their energy consumption is high. Second thing is that we have more of urbanization there. So more of urbanization, more of product consumption, of energy consumption. So these things are actually interlinked. Similarly, we see that we have also increased transportation sector, energy consumption, transportation sector. As the GDP increases, the logistics increases, the movement of goods, vehicle, these things are increased. So they also add up to their part in the energy consumption by different sectors. So I think most of you have now clear idea about how this GDP thing is actually very much interrelated with the energy consumption thing, and make it a point that if GDP of any region increases, it has a direct impact on the energy. we have seen with different examples also USA, China, India, and these examples we can see the states of India similar trend is observed in the Indian states also. Let's see if anybody wants to join. Almost. Yeah. We have one statement and we have a statement here, we have a conclusion here, and based on this statement and conclusion, uh, there are two conclusions actually, A and B. So based on this statement, two conclusions are there, and you have to mark which of these are actually true. The statement is that let's see, somebody wants to join. Okay. So we have a statement here and we have two conclusions that follow these statements. We have to determine which of the options are correct. So for these type of questions, first see what the statement is telling you. Okay. So statement is basically Maharashtra consumes more energy than Tamil Nadu. So it is talking about that Maharashtra consumes more energy. Then that based on the trends usually seen in the relations in energy usage and economic activity. So when we talk of economic activity, you can think it in terms of GSDP, gross state domestic product. It's a subset of GDP, but basically by states of India. Okay. So Maharashtra has more GSDP than Tamil Nadu. Tamil Nadu has more industrial output than Maharashtra. Okay. So if we see the last slide, we have seen that these different sectors contribute to the energy consumption, and as the GDP increases, their contribution also increases. So Maharashtra consumes more energy than Tamil Nadu. If this is the case, then certainly that if Maharashtra is consuming more energy, then Maharashtra has more gross state domestic product than Tamil Nadu. The statement one can be taken as correct. This is a correct statement. Tamil Nadu has more industrial output than Maharashtra. Okay, if we see the different contributors of GDP in energy sector, residential, industry, and transportation. So it cannot be said that only industrial output has increased, that's why GDP has increased. It can be from residential sector or it can be from increase in transportation also for this energy consumption. So this statement cannot be followed. So certainly conclusion A follows. Maharashtra has more GDP than Tamil Nadu. Tamil Nadu cannot have more industrial output than Maharashtra because GSDP of Maharashtra is more than Tamil Nadu. Okay. So if we see the different states ranked in India according to the GDP, I think the first one is Maharashtra. It has maximum first rank. Maha. Then there comes UP and I think Gujarat or something. Then we have this Tamil Nadu and then some state. Okay, so you need to remember maybe the question can come in the exam that key arrange these states according to their GSTP. Okay, so please remember this type of graphs and tables if it has been given in the slide. So the question can follow from these graphs and table very easily. So you just have to make a mind that if Maharashtra has more industrial output, then certainly more industrial output, more urban-based state, then certainly it would have a more contribution to the GSDP than any other state. So another thing is that if we see this graph for India, It's telling about the GDP and the energy usage relation for India. Okay, so units are missing here. Maybe this is the energy usage, maybe in megawatt or something, and this is the GDP, maybe in billion rupees or something. So units are missing here. So make sure these units are according to the GDP and energy usage. So if we compare the energy usage and GDP of India from 1985 to 2015, we see that as the GDP has increased, GDP is basically shown by the blue line. So as the GDP has increased, the energy usage has also seen a linear increasing trend. So from this graph itself, we can interpret that GDP has a more significant role in determining the energy usage that is coming for India, and with the different years of existence or determining the GDP, we see that much more uh, uniform increase in both is seen. So, uh, uh, particular conclusion can be drawn from this graph itself. Okay, forget about the units, forget about the quantities. From this graph itself, you can easily figure it out that if GDP is increasing, then certainly the energy usage will increase. Okay, as seen from this graph. Similarly, for if you see for different states also, for different states like Maharashtra, UP, Tamil Nadu, Gujarat, which are highly industrialized, high contribution to the GDP of India also. So a similar trend can be seen for these states also. Okay, so this data is basically taken from World Bank, and this data has been this graph has been taken from slides and weekly slides. So I put it here just to make you understand that how much these things are interlinked to each other. You can have a fair idea about these things. Okay. So I think this question is over. If there are any questions related to this, because these were important concepts which needs to be discussed. So I think no one has asked any question. Yeah. We'll move to the next question now. Somebody seems to join. Okay, so we move to the next question now. So next question is basically for 40,000 years ago, atmospheric CO2 concentration was dash, and this is determined using bubbles of dash trapped in ice. So this question is basically you can say a memory question where you need to actually what you say memorize the different quantity that was present. But even if you don't have such sharp memory, you can apply your mind itself. Like for present, what is the present CO2 concentration? So it's 400 ppm. Okay, so the present CO2 concentration is around 400 ppm, 397 or 420 ppm, maybe very near to that only. So what can be the ppm concentration some 40,000 years ago? So ppm concentration even after the existence of earth has only come to today's unit 400 ppm, so it must be not more than 300 ppm. Okay, so you can easily say this is wrong, more than 600 ppm. Between 250, this can be a right and this can be a right option. Okay, maybe this I'm sorting out which can be right. More than 300 ppm not a possibility, so this can be a right out of these two. Another thing is that this is determined using bubbles of trapped in ice. So what can be bubbles of CO2 trapped in ice? So whatever, if CO2 is trapped in ice, how will you know the concentration? So how do you know the concentration of air? Any gas in air. So you know the gas molecules, how much amount of gas molecule is there divided by amount of air. So that's how you get the concentration now. So this has been determined using bubbles of air trapped in ice. Okay. So the bubbles of air has been recovered from the ice, and they has been examined properly using different sophisticated instruments and methodologies followed in labs, and they determined that after around 40,000 years ago this CO2 concentration was only 300 ppm. So even this increase is only 100 ppm. You first understood this point. So when this increase is only 100 ppm, it is contributing a lot to the greenhouse gas emission and global warming. So that needs to be understood. Yeah, maybe this increase is very small, but it is contributing a lot to the global warming. It is adding a lot heat to the Earth atmosphere. So that's need to be checked. And mainly, this concentration was actually very much increased in the last 200 years after Industrial Revolution. So we have had more of industries, so these industries actually contributed a lot to this CO2 emissions. So whenever we see we can't be right, we can apply our logical sense to answer also. Okay? And these things are very important. You just have a fair idea also ki how much was the ppm concentration of CO2. So you can actually derive or have a logical conclusion that it must not have been more than 300 ppm, and must be air which has been trapped in ice, which has been utilized for uh, determining. Somebody wanted to join? No. Okay, which must have been utilized for determining the CO2 concentration. Now we move to the next question, which is glaciers are melting due to increase of CO2 percentage in the atmosphere. So this is a statement. We have two conclusions. So we have to actually determine which of these conclusions are right based on these statements. So glaciers are melting due to increasing CO2 percentage in the atmosphere. This is the statement. Okay. So we have increasing CO2. Main thing is that. So that's why glaciers are melting. It is saying that. So what can be the conclusion? So when glaciers melt, so first thing is that the temperature increases. This increase in temperature leads to melting on glaciers. So it must be that CO2 must be trapping the energy coming from sun. Not only the sun, energy that is released from the human activities also is getting trapped. Okay, so CO2 traps the energy which comes from the sun. Correct. Second thing is that ki earlier glaciers were not melting, but as the CO2 percentage has increased in the atmosphere, these glaciers started melting. This means that ki more CO2 in the atmosphere means more absorption of energy, and not only absorption of energy, whatever Earth reflects the energy back to the atmosphere is also getting absorbed by the CO2. So this is the global greenhouse gas or global warming phenomena. Okay, greenhouse is basically this thing. Ki whatever rays is coming to the earth and reflected back, this is getting absorbed. So this statement is also true. So conclusion A is right, conclusion B is right. Both are right. Okay, conclusion A and B both are right. So option A and B both is correct. Now we move to the next question, which is question 10. Talks about world total energy usage is same as the energy received by the earth from sun in. So we will calculate it also, but for now you can say that ki it's very fair amount, very fair, very minute amount. Okay, so world total energy usage is same as the energy received. So sun actually radiates a lot of energy, hell lot of energy to us, but and if we could trap this energy, only a significant small fraction of energy like 0.1 or 2% can fulfill the whole energy world's energy requirement. Okay, so this is basically 0.042 days, or I think 1 hour. If we trap the energy that comes from sun in 0.042 days or 1 hour, 0.042 days, 1 of 365 into 24. That's how we achieve 0.042 days. Okay. Correct answer is this. So how much is the energy received from sun annually? So let's see in the next slide itself. We will calculate this whole thing. How much is the energy received from sun annually? The professor has also explained these things much more elaborately in the slides. So you can go through slides also, and I will also uh, explain very briefly about how much is the energy received from sun annually and total energy consumption of the world. So let's see the different facts about solar energy. Let's have a discussion on solar energy itself. So this is the sun. Okay, and this is earth. So earth is basically very small compared to sun, and this is earth atmosphere. So sun is radiating the energy, but this energy gets reflected back due to various molecules in the earth. So whatever is energy received at the boundary of the atmosphere with outer space is basically a constant. This, why it is constant? It's this is variable term actually. It is termed as solar constant, but this energy is actually variable. But it doesn't vary very much according to seasons or different time of the day. So that's why it is termed as a constant, a type of constant. So its value is 1300. You must remember 1367 watt per meter square. This is the amount of energy that is received from sun by the earth every second watt per meter square for every square meter of area just outside the earth. Okay, so but due to the different radiation or different absorption, emission, transmittance of the various molecules in the atmosphere, only 343 watt per meter square reaches the earth. Okay, so this is the amount of energy that is actually received. So if you see, this is earth, this is atmosphere. Here on the brink of atmosphere it's 1367, but on the earth itself the amount of energy received is 343. Okay, so this has been distributed according to the surface area of earth. Doesn't mean that this point itself is receiving 3.43, every point on earth is receiving 343. It varies. Okay, so maybe Mumbai is receiving 743, okay, something 702,
maybe Ladakh is receiving 302 or 150 watt per meter square, or in night time it also varies according to day and night also. Another thing is that this energy is basically represented in per meter square, like per unit area. So we need to calculate the area of Earth. For that, we consider Earth as a total sphere. We know the radius of Earth, like 6,500 or something kilometers. So we can calculate the surface area of Earth. So surface area comes out to be 5 into 10 to the power 14 meters square. So total energy received from Sun on Earth can be termed as surface area multiplied with the irradiance. So it comes out to be 1715 into 10 to the power 14 watt. This much amount of watt is joule per second. So this much amount of energy received by Earth per second. Okay. But the main problem is that out of this energy received, 30% energy reflected. So we have absorbance, transmittance, and reflectance. So 30% is reflected. Earth doesn't take 30% of the energy because of the albedo values, and different structures like mountain, water, grass, everything present on the Earth. 30% is reflected. Another thing is that only 30% of the Earth's surface area is land and 70% is sea. So we can only utilize on land itself because we habitat on land. So accounting for this 30% is limited and only 30% is land. So usable solar energy comes out to be 360 into 10 to the power 14 watt or something very nearby. So various books or various slides mention these values in much different method of calculation. That is because they take surface area of Earth or some other every solar radiation as some other term. But the concept is this only. Okay. So if you this is what is basically joule per second. So if we calculate it for annually, so what we do joule per second is that we multiply it with 3600 into 24 into 365 days. Okay. So we get the annual amount of energy received from Earth, from Sun. It is around 66 into 10 to the power 22 joules. And if we see 2018 data, our energy consumption was around 6 into 10 to the power 20 joule. Okay. So let's say we divide this two numbers, 6 into 10 to the power 20 and 6 into 10 to the power 66 into 10 to the power 22. Okay, so we see that as we divide, this comes out to be 10 to the power 2, this comes out to be 11 or something. So we see that only this fraction is only 0.1%. So our energy consumption is basically 0.1% of the total annual energy received from the sun. So if we could harvest only 0.1% of the solar energy, we have enough energy supply for the whole mankind for the whole year. So you can imagine how much is the energy that is received from sun. So basically what happens is that this energy is very much in variable form, received at a variable rate, intermittent nature, and various other things are there. But if we have a device that could capture all of these energies, then it can fulfill all our energy needs. We don't need to burn fossil fuels, we don't need to have this greenhouse gas emission, ozone depletion, everything. Most of the problems regarding atmosphere will be solved because of usage of the solar energy itself. Okay, so I think you must have got a fair understanding of these things, facts about solar energy. So I've tried to explain it a more elaborative way, so you guys can itself calculate how much is the solar energy received, how much is the our energy consumption, and what percentage of solar energy we can harvest to determine the energy usage. Okay, so I think this is okay. So we move to the next slide. So our next slide is basically what are the various options possible to maximize the energy received by a planet from its star. Okay. Okay, so if you see this question, it's asking about okay, what can be the various. We have a star. We can harvest energy, but what can be the various options possible to maximize the energy received by a plant from a star? So it is not talking about energy only. It is talking about maximize. So another thing is that key, as we have seen in the last question, if surface area of Earth is increased, so more energy will be harvested here. Let's say instead of 5, it is 10. So we will multiply it with 10 here. This whole amount will get into 2. So 1750 into 2. Okay. So the increase in surface area exposure to the planet also increases the amount of energy saved by a planet from a star. Another thing is that bringing the planet closer to the star doesn't help very much because only the surface area of the planet can have an impact even if the planet gets very nearer to the sun. So maybe it can so yeah, sorry, this sun, so this earth is situated here, so it has an average radiation of 343 watt per meter square. But if this earth is situated here, maybe it has an average radiation of 1000 watt per meter square. Okay, so yeah, if we increase the surf sorry, we can increase the surface area or we can increase the average solar radiation received on the earth. So as the planets move closer, this can also be a option to increase the maximize the energy power. Another thing is that we surround this sun with a Dyson sphere. So we will trap all the solar energy emancipating from the sun. So that's how this can also be utilized. So using Dyson sphere method is also true. Moving planets farther from the sun. So as we move farther from the sun, this 343 will become 170. So what it will do? It will minimize the energy received by a planet from a star. Okay, so this is not true. So ABC is true. Another thing is that have you remember the Dyson sphere? We talked about it in question 3 or 4. So recall what a Dyson sphere. This is a star. So we surround this with an imaginary hypothetical sphere that receives the energy generated from the star and utilize it for the different purposes. So that's how it has been imagined, this Dyson sphere thing. Okay. So this whole solar energy thing cannot be um, uh, um, cannot be proper or properly discussed without discussing the Earth's energy budget. So we'll discuss this energy budget. Like we have this budget in February 1 or 2. Our finance minister present the budget. So whatever is received by the government, where the receivings are going, where the government is spending. So we need to have a plan, like how much is received, how much is going out from the government's hand. So that's how a budget is actually envisioned, and it is very useful in determining our usage. So we will study this Earth's budget, but it is not Earth's economic budget. It is basically energy budget. So we will have a discussion after a few slides because I want you to spend more time on this understanding this Earth energy budget. Okay, so let's see if someone wants to join. Okay, no one wants to join. What is going on? Okay, so let's move to the next question. After discussing these 3 4 questions which are remaining, we will discuss the energy budget. The question is temperature of sun surface is approximately. So first understand the question. It is not asking about sun's center's temperature. It is asking what is the temperature on sun's surface. So whatever is temperature on surface is very much different from whatever is the temperature in the sun's core. Okay, maybe here it can have a 50,000 or 1 lakh degrees Celsius, but at the surface, due to various phenomena like radiation, heat transfer, and other things, this temperature is quite low compared to the whatever the temperature is in the core. And also because of fusion reaction, more energy is produced at the sun core. That contributes to the very high rise in the temperature in the sun core. Okay, so temperature of the sun surface you need to remember it because this is basically a memory based question. So temperature of sun surface is approximately it's something around 600 Kelvin, 6000 Kelvin, sorry, 6000 Kelvin. So how much is 6000 Kelvin? Subtract 273 Kelvin from it. So it comes out to be 5727 or something, okay? 5727 degrees Celsius. So yeah, it's something around 5500 degrees Celsius. And similar in magnitude to the welding temperature attained in arc welding. So we'll discuss arc welding also. It's similar temperature arc welding. It approximately constant. Yeah, it's overall the surface throughout the surface of the sun. Full temperature is approximately constant. So what happens in arc welding? We have a cathode and anode, and due to this, very high temperature arc is formed, electric arc is formed, and this temperature in the core of this arc can be as high as 5500 degrees Celsius. Okay, and due to the high temperature, the surfaces melt and join together, fuse together, or something. Okay, so this is how the arc welding is actually utilized. So I've put most of you have seen this arc welding because this is very common type of welding being practiced by every welder nearby your house. You must have seen. So one welding is gas welding, another welding is arc welding. So there are different types of welding like plasma arc welding and similar types of. They must be knowing. There are different types of welding which are actually practiced like submerged arc welding, electric arc welding, gas welding, oxygen, CO2 or something welding. So there are a lot of welding types. So one of these welding is arc welding. Okay, so we move to the next question. I think most of you have understood this question. This is basically one thing is that you need to remember the temperature of sun surface, which is around 6000 Kelvin. So based on 6000 Kelvin, you can similarly say that similar magnitude to the welding temperature in arc welding because they have it also has a similar magnitude of temperature at the core. It's around 5500 degrees Celsius. And another thing is that throughout the surface of the sun, this temperature is actually very much constant with little variation due to solar spots or something. So I will not go much detail into what solar spot is. So I will leave you guys to actually go on Google and search what are solar spots, what are solar storms, how they are formed, how they affect the earth. So these are interesting things which you can search and get to know and add up to your knowledge also. Okay. Now question 13. So question 13 is that you need to arrange the following in their increasing order. So radius of Earth orbit, Earth radius, and Sun's radius. So if this is Earth, so this it's asking for radius of Earth versus the radius which the Earth rounds around the Sun versus the radius of Earth orbit. Okay, this is Sun radius Rs. This is Earth radius Re. and this is when we talk about radius of Earth orbit, it's generally taken from center to center. Okay. Based on your understanding, also you can answer. Based on the understanding of solar system, you can answer this question. It's not a very difficult question to answer. But in case you don't remember the values and you want the values, so I have put the values also. So Earth radius is basically 6371 kilometer. Sun's radius is zero point 0.7 million kilometer, very near to 6,96,340 kilometer. And Earth orbit around the Sun is 1.5 crore kilometer. Okay. So if we arrange it, so Earth radius is the smallest. So it will come here. There is the Earth is the smallest, so it will come here. So after that, Sun's radius, which is 6,96,000, then radius of the Earth orbit. Okay. So you just need to have a logical sense to solve this question. Not a very difficult question to answer. Sorry, if anybody wants to join or if anyone has asked any question. No, nobody has asked any question. So seems that most of you have understood the concepts simple way. So if you want you want to ask any questions, so you can unmute your mic and ask. Otherwise, you can also post the question in call messages. So like this, Vishal has asked about how why planet move around sun. Please explain more about the energy properties. We will discuss about this also. Similarly, you can post your questions here. So if there are no questions, let me move to the next question. So next question is that at any given point of time, one side of Earth radiates energy obtained from the sun back to the space because so if we see the Earth, this is the Earth and this is the sun. Earth rotates on its axis. Okay, so Earth rotates on its axis and also revolves around the sun. So what happens that only one portion of Earth actually receives the sunlight. Okay, so this portion becomes heated. So when it goes to the other side during the other half, like other next 12 hours, so this heated portion actually radiates energy. Okay, so what is the apparent reason? Because it is a night side on the earth. Sun is this side is not facing the sun. So because this is hot, then this part, so it radiates energy. Okay, and also this temperature is more than, so A is also correct, B is also correct. Temperature side of earth because this side has actually taken the energy. It moved after 12 hours. It moved to this side, and this is hotter. This is actually taking energy back. The surface of other star is less than. No. This is not the correct answer. Moon is hotter than sun. This is also not the correct answer because it radiates energy. There is no such phenomena as conduction or convection taking place. Okay? So Moon is situated at 384,000 kilometers far away from the Earth. Okay? Now question 15. Intensity of sunlight incident on Earth is higher during the intensity of sunlight incident on the Earth is higher during dash than dash of the day, and therefore a device captures dash light during part of the day. So just understand and put these options here. see if this makes sense. Okay. So intensity of sunlight incident on Earth is higher during the middle than morning. So this is okay because in the middle means noon. Okay, sun is overhead, so yeah, it receives more sunlight than morning because at morning sun is at slant. There is a slant morning and evening. So sunlight is more middle than morning, and therefore a solar device captures more light during that part of the day. So this fits, and certainly this is correct option. During the evening, then middle. So I think during the this cannot be correct option because if, at morning and evening the Earth receives much less radiation than middle. Okay, because sun is overhead in the middle. Okay, so in morning then middle, this is also wrong. Middle then evening, then therefore more light. So this is also correct because in middle at the middle the earth receives intensity of sunlight is more than evening. Okay, so in the noon, basically what it talks about middle is basically noon. So the intensity of solar radiation received is certainly more than what it is received in the morning and what it is received in the evening. Okay, so correct answer is A and D. I think it's over for today's, but we need to have discuss of an earth energy budget. So let's take a break of 2 minutes and then we will discuss. So I let's have a discussion. Let's say if anybody wants to ask question. Oh, no questions. Seems like most of you have got through the weekly lectures and understood the concept very beautifully. So if you have not gone through the weekly lectures, I will suggest that you guys should put once at least once through the weekly lectures. So you guys can have a good command about different things, different concepts which is being discussed by the professor himself. Okay, so let's discuss this earth energy budget. Then we will certainly end this session and meet in the next live session. So what is talking about budget? A budget is basically incoming and outgoing. So we uh, count for the incoming things and we count for the outgoing things and make a list of things and see that um, how much we are receiving and how much we are giving. Okay, so whatever we are giving must be out of this whatever we are receiving. We cannot have something extra. We cannot produce anything extra. So government cannot produce anything extra. Whatever it is receiving money, so it will give out that money itself. So that's how budget are accounted. So let's start from here. So incoming solar energy 174 PW. Okay, so let's take it as 100%. So as the incoming solar energy enters the earth, the first thing is that out of this atmosphere reflects 6% of this energy. Okay, so 6% is gone. What is remaining? 94%. Okay. So remaining is 94%. Then it next thing is that 20% is reflected by clouds itself. Okay. So whatever is remaining, subtract 20% from that, 74%. So 74% is remaining. We still have 74% of the incoming solar energy. Then as it goes down, 4% of energy is actually reflected from the earth itself. Okay. So 4% is gone now. So 70%. Okay. So how come only 51% is reaching here, absorbed by land and ocean? Then what we see that 16% is absorbed by the atmosphere. Not only atmosphere reflects, it also absorbs some of the sunlight. So subtract 16% from here. So we have 54%. Not only clouds reflect 20%, it also absorbs 3%. Okay, so subtract 3% from here. So remaining is 51%, which is received at Earth's surface and get absorbed by land and oceans. Okay, so you got to know how this 51% is coming. So if we calculate out of this 174 PW, 51% is 89 PW. Now out of this 51%, which is absorbed by land and ocean, coming was 100%, but due to various losses and absorbance, only 51% has reached the surface. Out of this 51%, it will reflect back to the atmosphere and sun. So out of this 51%, 7% goes from rising air. Okay, so remaining is 7% goes to rising air, 23% goes to the latent heat in the vapor, 50%, 15% goes to the radiation absorbed by atmosphere, and radiated directly to space is 6%, and similarly we have 64% radiated to space from clouds and atmosphere. Okay, so that's how this energy budget of Earth has been defined. Various distribution of incoming solar radiation to whatever is absorbed, transmitted, reflected by the different components on the Earth. So this has been calculated, I think, by NASA, and this has been presented as energy budget. It can vary also. This cannot be taken as constant. Maybe some variation also, point minute variation, but this is a very beautiful way to understand where the energy is coming and how much is the energy going out from the Earth. Okay. So I think most of you have actually okay, no questions. No question. So I think we have actually discussed these things. So thank you. Thank you all. And if there are any queries, you are always welcome to post your queries, or you can mail me at this email ID to 1418002@itb.ac.in. Or else, I will suggest you to post your queries in the discussion forum itself. And also, I was checking the discussion forum, so somebody was suggesting that the live session can be shifted to Wednesday or Sunday. So actually, these live sessions are very much planned according to our timings and whatever the available slots are there from the NPTEL side. So you are actually free to join any live session. So we have one live session on Monday. Also, we have two live session on Tuesdays. So that's why we conduct three live sessions, so that you guys can distribute among yourself and find your convenient time to join the live session. Okay, so even if you miss the live session, so this is not a big problem, because these live sessions are actually recorded and they are uploaded in the YouTube. So I will suggest you guys to go to the problem solving tab, click on the YouTube link, go through the live sessions on the YouTube, and after going through the live sessions, you can post your queries there also. I will suggest you to subscribe my channel also on the YouTube, so that whenever I post any video regarding the live session, you get a notification from that. Okay. So see you guys in the next live session for on the next Tuesday. Okay. So this is